Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about mesh non-orthogonality in computational fluid dynamics. So to start with an overview of what I'm going to talk about today, I'm going to start by introducing what is non-orthogonality. I'm then going to move on to talk about how non-orthogonality is treated differently by different CFD codes such as OpenFOAM, ANSYS Fluent and ANSYS CFX. And then to finish off, I'm going to talk about why non-orthogonality is important in CFD solvers. So to start with some background, what we need to do is consider two cells in our mesh that are connected by a shared face, as you can see in the diagram. And it doesn't matter whether these cells are hexahedra, tetrahedra, prisms, polyhedra, quadrilaterals, it doesn't matter as long as the cells are connected by a shared face, which you can see there in red. And the two cells that we're going to think about have a cell centroid, which you can see from the dot in the diagram. And this is the setup that we're going to use to understand what non-orthogonality is in a mesh. So firstly, we need to think about the vector that connects the two cell centroids across this shared face. And that vector is going to be given by the vector D, you can see there in the diagram. And then the other component we need to think about is the face normal vector N, which you can also see there in red in the diagram. Now, the face normal vector is always perpendicular to the shared face. And as you can see from the diagram, this means that the face normal vector does not necessarily align with the vector that connects the two cell centroids across the shared face. And this really is the origin of where mesh non-orthogonality comes in. So mesh non-orthogonality is defined as the angle between the vector connecting the two cell centroids across the shared face, D, and the unit normal vector N. And we're going to give the non-orthogonality angle the symbol theta, which you can see there in the diagram. And if we want to compute theta, we can use a rearrangement of the standard cosine rule, which you can see there in equation 1. And what we do to get the mesh non-orthogonality is we take the dot product of the vector D with the vector N and then divide by the magnitude of these vectors so that we normalize them. And as you can see from this diagram, non-orthogonality is a quantity that's evaluated on cell faces. So the cell we have may have multiple faces, particularly if it's a polyhedra, and each of these faces, if it connects the cell to another cell, has a non-orthogonality angle associated with it. And this we're going to term face non-orthogonality, and it's the metric that's used by the CFD solver OpenFOAM. But it's not the only metric we can use, and that's what we're going to look at in this talk a bit later on. So just to give you some examples, if we have two perfectly square faces, which you could see there in the diagram on the left, then clearly the normal vector N is aligned with that vector D, and the non-orthogonality angle is 0. So we have a perfectly orthogonal face, which you can see there on the left. Now, as the cells become more skewed, which you can see there in the diagram on the right, that face normal vector N starts to depart from the vector D, and we get a non-orthogonality angle, which for the particular diagram I've shown you there, looks like around 30 degrees for the non-orthogonality angle. And usually for most CFD solvers can handle a non-orthogonality angle of less than 70 degrees. And as the orthogonality angle increases, it can become increasingly difficult for CFD solvers to get a stable solution. But for solvers such as OpenFOAM, a value of 70 degrees is often quoted as the maximum value you should really be aiming for with your mesh if you want to be able to attain a solution. So that definition of non-orthogonality angle that we've seen before does lead to some difficulties in some situations. And to give you an example of where such a situation might arise, have a look at the diagram there on the slide, which you can see. And what we can see is that these two cells, 1 and 2, aren't aligned with each other as they were in the previous example. And if you've constructed many meshes yourself, you may have found that you have cells in your mesh that align similarly to what you can see in the diagram. And again, what we do is we connect the two cell centroids with a vector D, which you can see there, and again we have the face normal vector n, which is pointing normal to the shared face. And what you can see from this diagram is that in this case it looks like the face non-orthogonality angle could be around 0 degrees, because it looks like the vector D and the normal vector n seem to be aligned in this case. However, as we can see just by eye, the two cells are far from perfectly orthogonal squares or cubes. And so in some instances we might want to use a different definition for the non-orthogonality angle to identify these cells when we're meshing. So an alternative choice to the vector D would be to use a vector that connects the cell centroid of cell 1 there to the center of the shared face rather than the cell centroid of the shared cell. And we're going to call this vector vector C, which you can see there in the diagram. And if we were to define a non-orthogonality angle based on the angle between C and N, we can see that in this case the non-orthogonality angle would be around 30 degrees, say, which by eye is a lot more accurate and appropriate than an angle of 0, which we saw before when we were using the vector D. So this is an alternative way that we could define a face non-orthogonality. Now this leads on to the treatment used by ANSYS Fluent and ANSYS CFX and some other codes. What these codes do when you're meshing and you're assessing your cells before you've run a CFD simulation, ANSYS will calculate the non-orthogonality angle for every cell, every face on the cell, using both the vector C and calculate it again using the vector D. So it calculates two different forms of the face non-orthogonality for every face on the cell. What ANSYS then does is it will take the largest of these angles for the entire cell. So again we have two computations of the face non-orthogonality for every face on the cell, and we take the largest of all of those non-orthogonality angles and we define this as the cell-based non-orthogonality. So each cell will have one value of non-orthogonality rather than several, as we would if we were using a face non-orthogonality treatment. And then what ANSYS then does is it will normalize these values, because a non-orthogonality angle will take a value between 0 degrees and 90 degrees, and ANSYS products normalize this to give a value between 0 and 1 and term it the cell-based non-orthogonality quality, as ANSYS solvers like to use quality rather than absolute values of angles. And of course in this instance a non-orthogonality angle of 90 degrees will give a quality of 0, whereas a non-orthogonality angle of 0 degrees, or a perfectly orthogonal face, will give a cell-based quality of 1. So when you're constructing your CFD meshes and analysing their quality, take care to look at, am I looking at a cell-based non-orthogonality, or am I looking at a face-based non-orthogonality? And these two treatments are both fine for meshing, because ultimately when we mesh, what we want to do is identify the bad cells in the mesh so that we can improve, restructure and refine them and lead to a better computation. However, when we then proceed to the computation, it's really the face non-orthogonality that we care about and that has an effect on the solution, and that's what we'll see in the preceding slides. So to understand why non-orthogonality is important for CFD solvers particularly, what we need to do is consider the finite volume discretization of the diffusion term specifically in the Navier-Stokes equation. So if we consider equation 3 there, which is the unsteady, incompressible Navier-Stokes equation, and the diffusion term is highlighted in red there for you. And when we take the finite volume discretization of the Navier-Stokes equation, we consider the finite volume discretization of each term one by one. And what we're going to do is look specifically at the diffusion term, which you can see there in equation 4. And the finite volume discretization is a volume integral over a given cell in the mesh, equation 4 there. And if we want to proceed on and simplify this term so that we can transform our finite volume integral into a matrix equation, then there are a number of ways we can do this. And for those of you who aren't familiar with this finite volume discretization, I would highly recommend you go back and watch one of my previous videos where I've looked at this in a lot more detail, and you can find a link to that video in the description below and in my channel if you want to watch that. But anyway, to give a quick summary of how the finite volume discretization of the diffusion term works, what we do is we look at equation 5 and we use the divergence theorem, or Gauss's divergence theorem, to turn that volume integral into a surface integral. And when we perform the divergence theorem, what happens is also the nabla dot there gets replaced with the dot product with the face normal vector. Just a reminder, divergence theorem is telling us that the divergence of a quantity within a volume is equivalent to the flux of that quantity over the surfaces of the volume that encloses. And that's why we have a surface integral there and a dot product with the normal vector, because that's going to be the flux out of the cell. And because we have a polyhedral cell, it's a fixed geometry with regular faces and a set number of faces, n, we can proceed from equation 5, which is an integral over the entire surface of that cell, to the summation over the fluxes out of the individual faces of the cell. And as I've been through in the previous video, because we have a linear variation across the cells, we can take the value at the face center, that's the subscript f there, which you can see in equation 6. So the finite volume discretization of the diffusion term gives us a summation over all the faces f of our given cell of the kinematic viscosity nu f multiplied by the dot product of the velocity gradient, that's grad u, on the face, and the unit normal vector on the face multiplied by the face area SF, and we add those up for all the faces in the cell. Now what we want to do is proceed a little bit further, because we'd like to try and decompose this into a matrix term which we can add into our matrix equations. However, the difficulty specifically with the diffusion term is evaluating the dot product of the gradient of the velocity vector, that's grad u, on the cell face, and the unit normal vector n. Now, just a reminder of what situation we're looking at here specifically. We have our owner cell there and our neighbor cell on the left, and the owner cell, we know the velocity at the cell centroid, up, and for the neighbor, we know the velocity at that cell centroid, un. We also know the unit normal vector, that's n hat there, which is pointing normal to the face. However, what we don't know is we don't know the velocity gradient on the cell face and how to dot product that quantity with the unit normal vector. And that's a little bit more what I'm going to look at here. So if we look at the terms individually, the kinematic viscosity, nu f, on the cell face, we can get that term directly using some form of face interpolation scheme, such as central differencing or upwind differencing. And if you'd like a reminder of how we do that, general face interpolation schemes, I'd advise you to go back and have a look at my previous video on upwind differencing and central differencing for the convection term, and that should be straightforward, and you should quickly be able to see how we get the value of the kinematic viscosity on the face. Now, to evaluate the dot product of the gradient of the velocity and the unit normal vector, what we could do is, if that unit normal vector was parallel with the vector between the faces d that we see before, then we could evaluate this straight away and say that the dot product is going to be the velocity at the owner cell centroid minus the velocity at the neighbour cell centroid, that's the change in velocity, divided by the magnitude of the distance vector between them, that would be the grad u, and then multiply that by the magnitude of the unit normal vector n, and that would give us the dot product of those two quantities. However, what we've seen before is that the unit normal vector n generally isn't parallel with that vector d, and that's where the non-orthogonality concept arises. And here we can see the difficulty that's creating when we're trying to evaluate those terms, is that we can't just multiply the magnitude of the normal vector with the 1 over the magnitude of the vector connecting the cell centroids d. So what can we do at this point? Now, Professor Jasak in his thesis shows that the trick to evaluating the diffusion term is to split the unit normal vector n into two components, and the two components we're going to denote as delta and k here, and that's following the original notation used by Professor Jasak. So if you want to go back and have a look at his thesis, you should be able to follow along exactly. And what we're doing in this decomposition is that we're replacing that normal vector n by a component delta which is parallel with the vector d that connects the owner and the neighbour cell centroids. And then the remnant that's left over from this we're going to be calling k, and that's a non-orthogonal component. And by using this decomposition, we can see that we can move part of the way forward in evaluating that finite volume discretization. And the way we do that is by taking our original finite volume discretization given there in equation 11 and substituting for the normal vector, we substitute in delta plus k. And as we know from our vector calculus, we can then just split that up into two separate terms. So the term on the left there in equation 13, we've got the same finite volume discretization, but we've got the vector delta there. And then the term on the right, we've got the same, but we've got the vector k instead of the unit normal vector. Now the term on the left is going to be termed the orthogonal component that we can treat implicitly, and the term on the right there is going to be termed the non-orthogonal component, which we evaluate explicitly. So we evaluate both of these terms separately, and then we can add the components together. And don't worry if you're not really sure what I mean by implicit and explicit treatment, because I'm going to go through that in the next few slides. So starting with that implicit term with the vector delta, we've already seen how to evaluate this because delta is parallel with the vector d between the two cell centroids. What we can do is we can say the gradient of the velocity vector dot product with delta is going to be the difference in the velocity at the two cell centroids divided by the magnitude of that vector d, so that's the distance, that's the grad u, and then multiplied by the magnitude of this vector delta, because they're both parallel with each other. Now, the reason we can treat this term implicitly is that up and un are both unknowns. So remember here we're solving the momentum equation, so the velocity is currently unknown, and that up is really representing the diagonal of the matrix, and then the un, which represents the neighbouring cells around that cell, is going to give off-diagonal components in the M matrix. And for those of you who are not sure what I'm referring to, if you go back and look at my video on the simple algorithm, you'll see how we turn this into a set of matrix equations at the end. And so this orthogonal term we can treat fully implicitly, and when we treat the term implicitly, the Laplacian operator or the diffusion term tends to increase and improve the stability of the overall set of matrix equations when we discretize the Navier-Stokes equations. So the orthogonal component is good and is more likely to give us that converged solution that we're looking for. The non-orthogonal term, on the other hand, is different. So the non-orthogonal term we evaluate explicitly, and what that means is that the velocity there we evaluate using the velocities that we already know So that's the velocities from the previous iteration, or the velocities from our initial guess field if we're at the first iteration in our set of equations. And what we do is we substitute that velocity in and then evaluate the dot product directly with that vector k there. And this whole item here we add as a source term onto the right hand side of the Navier-Stokes equations. And what this source term does is it tends to increase instability in our equations and make them more likely to diverge. So what we can deduce from that is that we would like this non-orthogonal or explicit contribution to be as small as possible so that our equations are stable and we can solve them. And the way that we do that is by minimizing the non-orthogonality angles in our mesh, so that for those cells the non-orthogonal source term contribution is reduced and we have a more stable set of equations. And just a reminder to see why that's the case, if we go back to our vector diagram there, what we can see is that the angle between the unit normal vector n and that vector d, that's the non-orthogonality angle theta, is proportional in some way to the vector k, depending on how we define it. And so generally, as the non-orthogonality angle theta increases, as our mesh gets more skewed and we come up with a really bad mesh, we can see that the vector k is going to increase and keep increasing, and that vector delta there is going to get smaller. So as our mesh gets worse, theta increases, so k increases, and that means that our explicit non-orthogonal contribution term also increases, which makes the set of equations more unstable and more likely to diverge. So of course the takeaway from this is we want to get as good a mesh as we possibly can, and that will make our equations more stable as we expect. So just a small side point now on the treatment of this non-orthogonal correction term that's used by OpenFOAM. What OpenFOAM does when it adds that explicit non-orthogonal correction term, OpenFOAM will always add the non-orthogonal correction term to the set of equations. But what OpenFOAM will do is limit the value of that non-orthogonal correction term, and it will limit the value so that the non-orthogonal correction term is smaller than the value of the implicit term, which improves stability. And so by OpenFOAM offering this limiter, what it means is that for those bad cells in the mesh, if we have a normal mesh where you have a variety of reasonable cells with good quality, but then you have a few cells with really poor quality and high non-orthogonality, OpenFOAM will limit the strength of the source term that you add in those cells specifically, and it's limited to a value that will always be less than the orthogonal contribution, the implicit term. And the result of this is that in the cells where our quality is really low and we have high non-orthogonality, we're reducing the accuracy of those cells. And the reason we're reducing the accuracy is we're not adding all of the non-orthogonal contribution, we're only adding a limited fraction of it. So in our entire domain, for the majority of all of our cells, we're going to get a good solution and a stable solution, but in the one or two bad cells that we might have, we're going to introduce a bit of error. But the trade-off that we get for that is that we can converge and get a solution in those cells, which is better than not having any solution at all. And this is quite a clever way of doing things. What OpenFOAM also does is OpenFOAM gives the option of further reducing and restricting the amount of non-orthogonal correction that we add in those really bad cells. And OpenFOAM does this by introducing a coefficient called gamma, which is usually 1, and in almost all cases we'll take a value of 1 for gamma. However, if our mesh is really bad and we really want to try and drop that non-orthogonal correction as much as we can to try and force a solution, even though it won't be very accurate, the user can reduce the value of gamma, and this will improve the stability of the equations. So it's quite a clever approach. Now, just to finish off, I'm going to talk a little bit about non-orthogonal corrector loops, and this is the general way that we sequence our algorithm when we solve a set of equations that we know we need to do to solve the Navier-Stokes system. Now, if our mesh is good, then we're not going to use any non-orthogonal corrector loops, and you may see this in various user guides and user manuals that for a good mesh, non-orthogonal correctors are not necessary or not needed. And why is this? Well, the reason that we need some kind of corrector loop is, if we remember, that non-orthogonal contribution there used an explicit treatment for the velocity. So we use the value of the existing velocity field or the velocity from the previous iteration. So we need to have some existing velocity field that we use to compute that non-orthogonal contribution. Now, if our mesh is good, then as we iterate between our equations, the outer loops of our simple or piezo algorithm are sufficient already. And what that means is that when we compute a velocity field with the momentum equations, we can keep that velocity field and solve for pressure, turbulent kinetic energy, for example, temperature, species transport equations, and we can keep that same velocity field until we move around to the next loop or outer loop of that simple algorithm, when we compute the next velocity field and update our non-orthogonal corrector. And we do that if our mesh is good. That tends to be sufficient. However, if we have a bad mesh, then we need to do additional inner loops of the pressure equation to ensure that we can maintain a stable solution. And what does that mean? It means us solving for the velocity field, and then as soon as we have that solution for the velocity field, we update the value of the non-orthogonal corrector, and we just solve the velocity field again immediately, so that we can then update the non-orthogonal corrector, and correcting by solving the equation several times sequentially before we then move on to solve for temperature, for turbulence and other quantities. And really we only do this approach if we absolutely have to, if we have a bad mesh, because it slows down the simulation a lot. So don't worry if that went over your head a little bit. I'm going to give you an example so that you can see actually the sequence of equations that we would solve. So I'm just going to start you off with an example of what you would do for a good mesh in a simple algorithm type approach. And a good mesh could be when your maximum non-orthogonality is less than 60 degrees, say. And what you would do, as per normal, you'd solve the momentum equation first, to give you the velocity field, followed by the pressure equation. And at this point, you have introduced the non-orthogonal corrector using the value from the initial condition, but this non-orthogonal corrector is small, so we can just solve the energy, turbulence and other equations, and then go back to the momentum equation, solve that again, and proceed with that outer loop only, and just go through 1, 2, 3, 1, 2, 3 until we have convergence. Now, if we have a bad mesh, on the other hand, we have to introduce some additional inner loops. And how that might look is we'd solve the momentum equation, we'd then solve the Poisson equation for pressure, and what we would then do is solve the equation again sequentially, each time updating that non-orthogonal corrector term to try and improve the stability of the set of equations. So that really what's happening is that velocity field is getting closer to the velocity field that we use for the non-orthogonal corrector, and we're trying to reduce that error. And usually for bad meshes, somewhere between 1 and 3 non-orthogonal correctors tends to be sufficient, because any more and really we're going to be slowing down that CFD code by a lot, and it tends to not be worthwhile solving, as our solution will be of very low accuracy. And then of course we would then solve the energy, turbulence, species transport and other equations after that. So that's a comparison of the different types of loops you would do depending on the quality of your mesh. So just to summarize everything that I've talked about today, the non-orthogonality angle is the angle between the face normal vector, that's the vector n, and the vector connecting the cell centroids that are across that shared face, and that's the vector d. And the non-orthogonality leads to an explicit correction term which arises for the diffusion terms only in the finite volume discretization of the Navier-Stokes equations. And this correction is essential for us to achieve accuracy in our solution, but it increases the instability of the equations, and so we want the correction to be as small as possible. And the way that we realize this in practice is by making the mesh as good as we can, as you'd expect, to try and reduce that non-orthogonality. Now, if there's no way round having a poor mesh for whatever reason, for the geometry that you may have, for example, then there are ways that CFD codes can go about accounting for a few bad cells which have high non-orthogonality. And those methods involve adding limited corrections and adding additional non-orthogonal corrector loops to the overall algorithm. Now, a useful reference for those of you who are interested in some further reading or would like to dive into a bit more detail about the non-orthogonal corrections, how we choose that vector delta and the vector k, I'd highly recommend reading Professor Jasak's thesis, which has got lots of very useful information in it, and his thesis is available up online, and I'll leave a link to it in the description below. And also, for those of you who have continued again to watch to the end of my video, thank you very much for supporting the channel. I appreciate very highly all the feedback and comments you give me. They really do help. And as always, if you have any more comments or suggestions for things that you've liked in this video that you found useful, or other things that you might like to see in future videos, please leave them in the comments below. I do read through all of your comments, and I really do appreciate all of the thoughts and suggestions you give me. And for those of you who are looking for more information or would like to go into a bit more detail, I'd highly encourage that you check out my website, and there's a link to that in the description below, where you can find further resources. I've put sort of comprehensive summary notes for lots of my popular videos on there. If you'd like to, for example, quickly dive into an equation or quickly look at the algorithm, but you don't have time or access, for example, to the full YouTube video, you can find detailed notes and references on my website as well. You can also find some useful calculators on there that you can use for various applications, like constructing your initial mesh, and you can find links to all of my publications as well if you'd like some further reading. And as always, thank you very much for listening, and I'll speak to you next time.